Hello, I'm Grace Audette. I'm a mechanical engineering major in the class of 2025.
Hi, I'm Alex Brown. I'm also a mechanical engineering major in the class of 2024.
I'm Gabriel Brown. I'm a mechanical engineering major in the class of 2024.
And I'm Abigail Clemence, a mechanical engineering major in the class of 2024 as well.
Throughout this presentation, we'll be discussing a few types of manufacturing systems and their components. Specifically, we will focus on reconfigurable manufacturing systems. Next, we will discuss two case studies of applications of reconfigurable manufacturing systems in the industry, and we will end with a discussion on any future applications of reconfigurable manufacturing systems with the development of Industry 5.0. First, what are manufacturing systems? Manufacturing systems are collections of resources, such as machines and tools, that transform raw materials into finished products. Manufacturing systems have two main goals. The first is efficiency, to produce the most amount of products in the least amount of time. And the second is cost reduction, to boost amounts of profits per product by reducing the amount of wasted materials. One type of manufacturing system is a dedicated manufacturing system. Dedicated manufacturing systems, DMSs, or dedicated manufacturing lines, DMLs, produce one part or product over a long period of time at a very high volume. These systems are designed to mass produce these parts or products at a low cost and high throughput. These systems are designed with inexpensive fixed automation, which means the initial investment is relatively low compared to other systems. When product demand is high, the cost per product or part is low. With a higher demand, the system allows the company to lose sale opportunities. With constant changes in market demands and competition leading to rapidly changing products, DMSs become less effective and profitable than other manufacturing system types. The next type of manufacturing system is a flexible manufacturing system, or FMS. Flexible manufacturing systems are able to produce a wide range of products on one line with lower throughput. They contain automated, numerically controlled workstations connected through a handling system managed through a central control unit, which can manage resources to manufacture a wide variety of parts. These systems contain general-purpose, computer numerically controlled CNC machines that can be adapted to use different parts. These systems are more effective at managing resources and creating a variety of products with parts on the same line. CNC machines typically only use one tool at a time, which can therefore reduce the throughput and is less fast than DMS for the same investment cost. Overall, FMSs are more flexible than DMSs in a changing market, as they can adapt to new demands in the system and produce a wider range of products, but they do require higher investment over time and have a lower throughput. In order to gain the benefits from both dedicated manufacturing systems and flexible manufacturing systems, reconfigurable manufacturing systems were created. RMS combines the high throughput from DMSs and the flexibility of FMSs to be able to rapidly and efficiently adapt to changes in the market. In addition, this system is designed for rapid change through the ability to adapt the functionality and capacity of machines in the most cost-effective way in response to demand within the market. This chart shows the overlapping values of reconfigurable manufacturing systems alongside DMS and FMS, such as reduced cost and versatility and responsiveness, along with the dates when all of these systems were introduced. RMS has 6 principles that enable it to reduce the effort and time needed to produce parts and reconfigure, as well as reduce the lifetime cost and keep production high during changes in market and consumer demand. The first characteristic is modularity, which is the compartmentalization of manufacturing system functions into units that can be changed between different arrangements for the optimal arrangement. The second is integratability. This is the ability to integrate different modules into rapidly and precisely using hardware and software controlled interfaces that facilitate communication and integration. Diagnosability is a system's ability to automatically read the current state of the system, to monitor product quality, and diagnose any problems to rapidly correct them. Convertibility is the ability of the system to transform the current functionality and adapt to new production and market requirements. Customization is within the design of specific machines or systems to keep the machine flexibility limited to a specific part or product family to increase customized flexibility. Scalability is the capability of the system to add or remove system components or manufacturing resources to modify production capacity. All of these 6 characteristics work together to produce an RMS system, which creates the highest efficiency, scalability, and flexibility for the system.
So the first case studies we looked at are about body and white manufacturing. Body and white manufacturing is the manufacturing process for creating the general frame of the car. Almost all the parts here are welded sheet metal parts that, and we'll be looking at the fixturing over here of the parts for the body and white. of the car, and that's a lot of fixturing for spot welded components. Traditionally, fixturing for the body and white parts to be welded is not modular at all. It's not flexible, so you can only they're only made for one specific model of car, and so you can't reuse them. You can't adapt them to multiple models of car. But with reconfigurable manufacturing, there are some tools that help us out. We've looked at 2 case studies of flexible fixturing. And so with flexible fixturing, that means that you can reconfigure the fixturing so it can adapt to multiple models of vehicle. You can also make adjustments, and you can also actually reuse a lot of the frame of the fixturing or various elements depending on the strategy that we'll talk about a little bit later on. The first case study used what they call the box joint system. Typically, the frame is made out of welded square tubing, but here they clamp together the square tubing using machined steel pieces like this with screws in between. And this allowed them to construct the frame of the fixturing very rapidly and quickly. But it also, the downside of this is that it's not accurate at all. So to compensate for this, they created what they called flexipods. So attached to the inaccurate clamped together square tubing frame, they have these modules that have 6 degrees of freedom. So they can rotate 3 ways, and they can also move translationally. And they also have the interfacing geometry over here to actually like locate the part onto, because that's critical as well. And these take a while for them to set up, but it helps compensate again for those inaccuracies in the clamped together frame. And about the performance of the system, they measured that the setup time in total was 16 hours, which isn't insignificant, but it's also, you have to keep in mind that when the frame is being welded together, that also takes a significant amount of time. And then to reconfigure it for a different model of car, then it only took 5 hours, which is pretty impressive. And then to adjust and tune the flexipods, which are sort of complex to do, took them 1 hour, but then they noted that that's a very high skill task. So when you're designing them, you have to make sure that there are good points to measure off of it, so you can actually adjust it correctly. And they, at the end of the paper, they conceded that higher quantity of volume tests need to be ran for it to be applicable in a factory setting. Second example has some similarities. They've tested out the interior of a car door for their spot welding assembly, and they have a cell over here that has a human worker and a robot worker. The human worker's job is to load the parts onto the fixture plate, and then it rotates around so the robot can weld it, and the human can load another one in. How they made their fixturing flexible is they have a base plate over here with tons of holes in it, and then there are different posts that have clamps and interfacing geometry and locating geometry on it to actually secure the interior of the car door onto. And this way you can reuse the same fixture plate and then just put different posts like these onto it for different types of car doors. And they saw a really impressive improvement. They did it for 2 types of car doors. You can see the 2 types over here, and the improvement they had. They almost halved the cycle time of both of them, and the robot utilization went way up. That was mostly because of the rotating aspect of it, but that was also impressive. And then the number of components for a single shift also. So,
All right, so a second case study we identified was titled Implementation of Reconfigurable Manufacturing Systems, the case of the Lego Group. And in this case study, they dived into how the Lego Group approached considering a new manufacturing system. So in an ever-changing, chaotic and competitive global market, manufacturers have been attempting to discover new concepts and systems for manufacturing to keep up and remain competitive with other companies. This paper examined potential areas of manufacturing processes that would be the most fitting for implementing RMS within. A literature review was then written and outlined in the case study to describe the benefits and main characteristics of RMS. Then the case study goes into a conceptual model that was created to analyze the most appropriate areas for RMS to be used within the Lego Group specifically to maximize the benefits within the company. Finally, a conclusion is formed from the analysis collected through the developed conceptual model. Responsiveness, capacity, functionality, and cost are the 4 features which define the difference between RMS, FMS, and DML. RMS is able to make a rapid and cost-effective response to market changes globally. In addition, RMS is dynamic and is able to change both capacity and functionality in response to these market changes, which shows a great advantage in the adjustment of capacity and functionality. RMS is also super scalable and at non-constant rates that depends on the initial design of the RMS and the changing market situation. Compared with FMS and DML, RMS will not be more expensive. Unlike DML and FMS, RMS can be reconfigured and more elements can be added to increase the functionality or capacity on the same system instead of more machines in parallel or addition. Reconfigurable systems and their machines should be designed at the outset for reconfigurability. Otherwise, the reconfigurable process will be lengthy and costly and therefore impractical. To achieve this goal, RMS is required to be designed to possess 6 core reconfigurable characteristics, which include modularity, convertibility, scalability, integrability, customization, and diagnosticability. Based on a theory developed by Corin regarding the relationship between RMS core characteristics and system goals, a conceptual model was developed in order to analyze the most suitable areas for RMS implementation, shown by Table 1. The analysis shown in the table focuses on the 4 features of RMS as specified before: capacity, functionality, cost, and responsiveness. In each of the features, the relevant RMS characteristics were identified and narrowed down. The analysis will concentrate on each of the respective production areas. 1 will mark an area where a feature and principle of RMS is currently implemented in the production, whereas 0 will mark a feature and a principle where it is not. And the scale between 0 and 1 will mark areas and features in slightly or partly implemented, where 0.25, 0.5, and 0.75 are mainly used. The LEGO Group's production contains the 4 main processes: molding, decoration, assembly, and packaging. Values between 0 and 1 are given to have a better understanding. The 5 values of 0, 0.25, 0.5, 0.75, and 1 are mainly used to mark an area where a feature and principle of RMS is currently not partly, half, more than half, and fully implemented in the production of the LEGO Group. Table 2 shows the structured values that are shown in this model. This table shows that responsiveness has 4 determinants, while capacity and functionality each have 3, and cost has 5. By adding these determinants all together, a new table is created to show the respective values of responsiveness, capacity, functionality, and cost in the LEGO Group's 4 production processes, which are shown in Table 3. From Table 3, Table 4 can be created, which includes the percentages of the 4 features each process gathered. This shows the extent of the accomplishments these processes featured of the 4 categories of responsiveness, capacity, functionality, and cost. Table 4 indicated that because there are no results higher than 50%, there's a lot of room for improvement within the LEGO Group's production in regards to the advantages of RMS overall. Once again, it can be concluded that there is plenty of room for improvement in these RMS features for the LEGO Group's future production systems, but particularly in the area of decoration, while there's also room for improvement within molding, assembly, and packaging as well. All right, so to recap, we've discussed the main advantages of RMS based on a literature review and discussed the proposed conceptual model to analyze the most suitable areas of RMS implementation into the LEGO Group. The LEGO Group's case study analyzed the most suitable production processes for RMS within their company.
Well, there's already been a lot of application of RMS that we've seen so far in industry. There's a lot of future directions that RMS is going in Industry 5.0. One main application that's being seen more of in RMS is sustainability. Sustainability is a huge focus of Industry 5.0, and integrating sustainability with reconfigurable manufacturing systems and optimizing these reconfigurable manufacturing systems for sustainability is a big area of research. One concept specifically being researched here is mathematical models to more accurately model different energy uses and sustainability of a reconfigurable manufacturing system. There are a number of different models that are being used to measure exactly the amount of energy that, like, moving an object from one area of manufacturing to a different area of manufacturing takes, and then being able to optimize that mathematically so you can set up your modules in your reconfigurable manufacturing system in the most efficient way possible to make your process more sustainable. Not only does this save you energy, but it also saves the company money in the long term and minimizes a lot of cost. Another concept that's being reviewed and starting to be implemented with reconfigurable manufacturing systems in regards to sustainability is a green BOM. This is a new concept that's beginning to gain traction that involves having a BOM where you can see exactly how each part of your system affects the environment. There's different parameters like how much energy you use, how much you can reuse your systems, recyclability, that you can evaluate in a green BOM and then optimize your RMS based on the results of your green BOM. While the digital twin has seen a lot of new implementations in direct line manufacturing, it's just starting to see implementation in RMS. One way that this is really important is because to have a reconfigurable manufacturing system, you not only need a reconfigurable physical system, but you need reconfigurable software. And a lot of this requires that you have some kind of digital twin to model exactly what's going on, both in the physical space and in the software space, and then being able to reconfigure that. So a digital twin is a particular interest and use in a reconfigurable manufacturing system. This has really been made possible thanks to a lot of new Industry 5.0 techniques, such as Internet of Things sensors and cloud-based storage and 5G that allow the transfer of large amounts of data and all this sensor data to be collected from the physical systems to then be modeled in the digital twin. Another special use of the digital twin in configurable manufacturing systems is using digital twin to optimize the system. While a regular manufacturing system can't really change based on the feedback you might get from the digital twin, a reconfigurable manufacturing system can easily change, and this is one of its big strengths. You can take what you learned from your digital twin and make your RMS more efficient. However, there are a lot of challenges to implementing a digital twin accurately. These include things like actually transferring the vast amounts of data to wherever you're storing and analyzing that data, as well as then analyzing that data takes a lot of computing power, and it's something that is just starting to be done. And one of the main ways that this computing and analyzing of digital twin data is being done is with artificial intelligence. The use of artificial intelligence in RMS has been gaining a lot of traction, especially in implementing things like the digital twin, but also in regards to sustainability and just analyzing all the data and optimizing your system based on whatever parameters or feedback you might have and configuring it. Artificial intelligence can be used to reconfigure a system based on feedback from IoT sensors and optimize your setup of your reconfigurable manufacturing system based on feedback from the AI. This can have significant impacts in forming and utilizing an accurate digital twin, as well as optimizing system for sustainability. A recent study directly applied artificial intelligence to a reconfigurable manufacturing system in a much smaller scope by using AI to minimize the amount of repairs and tool degradation over time that happens within a system. And the study was very successful. The artificial intelligence was able to reconfigure a manufacturing system to use fewer modules at once, so that more modules could be having repairs done, having maintenance done, so there would be less tool downtime and less failures and broken tools throughout the manufacturing process. In the future, the small scope of this study is probably going to be expanded to other studies and overall artificial intelligence that can optimize your reconfigurable manufacturing systems for a greater number of parameters.
Thank you.